Okay, this question is about electromagnetic induction. It's about a conducting rod oscillating up and down with simple harmonic motion inside a uniform magnetic field. Now that rod is moving up and down through an area, and the flux through that area is changing, and so an EMF is being induced. Now here they've given us a graph of displacement against time, and you can see that that is a sine wave, and the time period is marked with a capital T here. Part A, part 1, it wants you to draw a graph of the velocity against time, and so when displacement is 0 with simple harmonic motion, when displacement is 0, velocity is at a maximum, so velocity is at a maximum at the equilibrium position, so at time t equals 0, velocity must be at a maximum. When the when the displacement is at a maximum, that's at the amplitude, then the velocity is 0. When the displacement is at 0 again, then the velocity is at maximum, but in the opposite direction, and so on. And so you'll get a cosine wave with the same frequency as the displacement wave. Something like that. Now, for part 2, it asks you to draw a graph of the EMF generated against time. So the generation of the EMF, remember, is about the changing magnetic flux going through that area as it's moving, and the EMF is proportional to that change in flux. So the EMF generated is going to be at a maximum when the bar is moving as fast as possible. Now remember, because of Lenz's law, the current generated is going to oppose any change that causes it. So when velocity is maximum up here, EMF is going to be a maximum but in the opposite direction to the existing magnetic field, so we can say that's negative there, and then it will have the same frequency again, and it will be a negative cosine wave, something like that. Now it doesn't actually specify the direction of the magnetic field in relation to the direction of the uniform magnetic field in relation to these graphs, so you would still get marks for doing a graph that looks exactly like this for the EMF. You don't have to start at the negative. Now for 7 part B, we've got some information here and we have to make a calculation. We want to determine the magnitude of the maximum EMF between the ends of the rod. Now we've already said that the maximum EMF is going to happen when the bar is moving at a maximum velocity. So first of all, we need to find out the maximum velocity. Now here I've got my simple harmonic motion page of my data booklet, and I'm looking down and I see an equation for velocity here. Now, velocity is going to be at a maximum when the time here equals 0. Now, remember our graph that we drew before, velocity was at a maximum at time t equals 0. So when time t equals 0 here, then cos omega t equals 0, and so that's when the velocity here can be at a maximum because cos of 0 is 1. So the velocity max is equal to omega x naught times cos omega t, which is 1. So velocity max is omega times x naught, which is the amplitude. Now omega is 2 pi f, so that means that V max is 2 times pi times the frequency, which is 2.5 hertz, multiplied by x naught, which is the amplitude, which is 8.2 times 10 to the minus 2, times 1. So that gives you a Vmax of 1.29 meters per second. Now the EMF generated at that particular velocity is given on another page of our data booklet. This one over here, subtopic 11.1. And EMF is the magnetic field strength times the velocity times the length of the wire that's within that field. So E equals BVL, and E max is B times L times V max. So that gives us the magnetic field strength, which is 58 microteslas, 58 times 10 to the minus 6, multiplied by our Vmax, which is 1.29, multiplied by the length of the rod, which is 0.18 meters, and that gives you a maximum EMF of 13.5 times 10 to the minus 6 volts, or 13.5 microvolts. And that is your final answer.